and that's wrong. Okay, that's wrong. You can't do that. You have to know, or you have to combine both the normal stress and shear stress. And in this course, we're going to show you how. Okay, you cannot just ignore it. Okay, that's just plain wrong. That's just plainly incompetent. Okay, unfortunately, that's the way I was taught as an undergrad, and that's wrong. Okay, right. So you can see that there's a lot of layers that you have to learn in this course already. Okay, there's a lot. So now the thing is, if we go back to the question, okay, using point B together with the maximum shear stress criteria. Okay, so in about week 9, we're going to learn about all these criteria, but I'm going to talk about the maximum shear stress criteria. Okay, so again, this is just an introduction. Okay, this is the expectation that I'll expect you to know when you finish this course. As I said, this is a final exam question in the term that's just over, which is winter 2023. Some of you will ask me, Eugene, what is the class average for winter 2023? The class average was 61%. Okay, right. So now coming back to here. So now let's look at what do we mean by the maximum shear stress criteria. So the maximum shear stress criteria is basically an equation. So is the maximum shear stress is equal to normal stress yield divided by 2. That's it. That is the equation for the maximum shear stress criteria. Okay. Now, if you look at this equation, it is a conservative approximation. Okay, and I have evidence to show you why. Okay, so if we were to go back to the material property on our previous slide, we go back to the material properties over here. Okay, so as you can see over here, usually we do tensile tests. Very seldom we do shear. Okay, one is because it's not always used. Okay, and tensile is very commonly used. If you don't have this value, so let's focus on 450. You can estimate the shear by 450 divided by 2. So this will be what? To 5. Or you have over here 690 divided by 2. So this is equal to 345. Like the case where it's 250 over here. We know now this 145 over here is we know this value, and this is from test. So, but if we don't have the value, you just put 250 divided by 2. This is equal to 125. So you realize that 125 is less than 145. If you test it, it'll be 145. If you don't test it, you use the maximum shear stress criteria, which is the yield strength divided by 2, you get 125. It's more conservative. It is better than what? Nothing. Okay, conservative is better than nothing. Okay, so that is what we mean by maximum shear stress criteria. Okay. So with this question, we are going to determine the magnitude of omega naught. So we want to know what is omega naught over here. And we have to determine the factor of safety. Now, before we go on to determine omega naught, let's talk about factor of safety. Okay, so let's go into factor of safety. Okay, let's go into factor of safety. And then I will quickly go into the textbook. If we look at the textbook, there you go. So you go to a certain page of the textbook. They did mention what is safety of factor. So we go here. I hope to find usually. Okay, here we are. So if you go into the textbook, okay, and I'm going to copy the textbook. formula. Okay, and I'm going to paste. Okay, and then I'm going to take our stress strain curve that we've drawn. We'll come here. I'm going to paste it by the side. This is our stress strain curve. Okay. So what they mention is the factor of safety. Okay, there are two ways that you can determine the factor of safety. Is the ultimate load divided by the allowable load, or the ultimate stress divided by the allowable stress. Now, so what you can see over here, the ultimate stress is in the what region? Is in the what? Plastic region, as you can see over here, right? And the yield is where is a transition between is at the transition between the elastic region and the plastic region. Okay. So if you look at this formula, it's quite worrying. Okay. Why do I mean by quite worrying? Is the ultimate strength in the plastic in the formula, this ultimate strength is in the where? Is in the what? Plastic region. Okay. So we have to be really, really careful with this. Okay. What do I mean by careful with this? We have to be cautious on how we apply this formula. And now I'll tell you why. If for brittle material, okay, for brittle material, the factor of safety is equal to stress ultimate strength divided by stress allowable. Why we can use that is because for brittle material, the stress ultimate strength is approximately equal to the stress use strength. Okay, so I'm going to write stress out US over here is the ultimate strength. Okay, so this is valid. This is okay because the ultimate strength is very similar to the use strength. So if you were to ask me, Eugene, then can you sketch out a brittle material? So I'm going to sketch the brittle material stress strain curve now. So brittle material, it has a much higher Young's modulus. You go up much higher, then it will just fracture because it's brittle. So if you look over here, down here, as you can see, this is the use strength. Okay, and this is the stress ultimate strength. So the stress use strength is approximately equal to stress ultimate. So this line you will see is for brittle material. Okay, it's fine. But when it's a ductile material, which we are dealing over here, so this is a stress strain curve for ductile material. Why I address this as ductile? Because it has higher percentage of elongation, or it stretch longer. Okay, so this is our ductile material. So as you can see over here, for ductile material, the right formula to use is factor of safety is equal to stress use strength divided by what? Stress allowable. Okay. Why is because the use strength is so much lower than the ultimate strength. Okay. So these formulas are not wrong. When to apply what? Okay. So this is number one already, or things that you have to learn when to apply what. As I say, the textbook is not wrong. The textbook is right if it's what? Brittle material. because the ultimate strength and the yield strength are approximately about the same. For ductile material, it's not. Okay, for ductile material, the ultimate strength is much higher than the what? The yield strength. Okay, so again, coming back to this problem now. Right? Why I elaborate of this? Because at the end of the day, we have to determine the factor of safety. Okay, so just a question like this, okay, just a few lines, you have to be capable of the analysis. Okay, we have a lot of layers down here. Okay, and I spent like half an hour. We have not even started the problem yet. We have just completed diagnostics of the problem. Okay, so now before we can carry on and we can I'm going to carry on how to solve this problem. Anyone, any questions so far? Anyone, please? Okay, I don't hear anything yet. I either you are okay, or you are sleeping, or you are awake and you are bored. But don't worry, let's carry on. Okay, right. So now we start solving this problem. Okay, so the next thing we have to find now is we have to determine. So the first thing we have to determine the bending moment and shear force acting. Okay, before I write the bending moment, I'm going to write mz and shear force Vy at point B. Okay, because this question very specifically says point B. So as you can see, I want you to observe something is what we call transformation. So what we see over here is transformation. So what you will see if I were to draw the transformation, right? So this is our x direction, this is our y direction. Over here, this is rotation about z. Okay, so we have to determine the bending moment, okay, mz, and the shear force Vy at point B. Okay, so before we can do that, we have to sketch out the free body diagram. Okay, we have to sketch out for the free body diagram. So I'm going to draw the free body diagram. Okay, so you have point A, and then you have point B, and you have point C. Okay, so what is the issue with this question is we don't know what is our L and what is L over 2 yet at this stage. Okay, so later on we have to determine our omega naught. So for now, we don't know what the values are, so we have to work in terms of L. Okay, so the next thing we have to draw the reaction forces. So we know AY has a vertical force going up, and BY at point B, you have a vertical force going up. Okay, so what we see over here is what we call as a pin, and over here we have what we call a roller. The difference is a roller, you allow it to go what? Left and right. You don't allow it to go up and down. For pin, you don't allow it to go up and down or left and right. Okay, so the next thing that we have is we have two triangle gradient distributed load. Okay, so next we have to determine what is our equivalent load. So over here, this is our equivalent load. Okay, so equivalent load. So the equivalent load is the area of a triangle. So this will be equal to half times base times height. So this is equal to omega naught L over 2. Okay. So on the other side, again, why only omega? Let's ease our